Okay, so welcome to the second session. So the first speaker of this session is Francesco Rescigno from University of Rome, and he will be talking about primordial black holes from supercooled phase transitions with radiative symmetry.
Okay. So, well, I am Francesco Rescigno, a second year PhD student of University of Rome in Tor Vergata University. And today I will talk about primordial black holes from the supercooled phase transition with radiative symmetry breaking. This talk is based on this paper that I published with Professor Roberto Salvio and Indra Kumar Banerjee. So, well, I will start from a brief recap about first of the phase transition and then introduce the two main tools that I will use to study the phenomenology of the first order phase transition, so the supercooled expansion and the improved supercooled expansion, and then apply this to the mechanism that can generate primordial black holes in first order phase transition, that is the late blooming mechanism. So let's start. Well, first order phase transition can occur in the early universe when the temperature T drops below a critical value. The finite temperature effective potential develops a new stable minima that we call true vacuum, while the old minima became metastable, that is the false vacuum. So the false vacuum eventually decay in the true vacuum, and it manifests as the nucleation of true bubbles in a background of the false vacuum. So we are interested in relative symmetry breaking models. So we start from the most general no-scale Lagrangian. So we include the gauge interaction, a certain number of scalars, wide fermions, there would be Yukawa interaction, of course, and the no-scale, the scalar potential that in a no-scale theory has this form here, but at quantum level, the coupling depend only on the renormalization group energy mu, and there may be some specific value, mu tilde, at which the potential would develops a flight direction that we parameterize with this field, scalar field key as follows. And along the flight direction, the potential looks as follows, where we define the quartic coupling in this way, such that, well, at value mu tilde, it vanishes. This is the definition of flight direction. So the one loop effective potential takes this form, where we define the beta function of the quartic coupling, and setting the scale equal to mu tilde, the quartic coupling vanishes, we get this nice form for the one loop effective potential zero temperature. So beta bar is the value of the beta function of the quartic coupling at the scale mu tilde, and K0 is the scale that is introduced by relative symmetry breaking. So when the condition of flight direction and the condition of and the minimum condition, so beta bar is positive, are fulfilled, then K0 is the zero temperature vacuum expectation value of K and is the new absolute minima of V. So the fluctuation around K0 develop a mass that is radiatively obtained that looks as follows. And with this mechanism, we can also break global or local symmetries and generate particle masses where K0 plays the role of symmetry breaking scale. So, for example, using this term here and defining the coupling in this way, so energy improving and set all equal to mu tilde, we get this expression here that evaluated at the minimum gives the tachyonic mass for the Higgs. Now, for a no-scale theory that we are studying, the thermal effective potential takes this form, where this is the zero temperature contribution that we studied, that we calculated before, and this is the thermal contribution, and here you can see the bosonic contribution and the fermionic contribution, plus a cosmological constant that will play no essential role in our analysis, but it can be included. Now, the two thermal functions, one for the bosonic degrees of freedom, the other for the fermionic degrees of freedom, are defined as follows, and can be expanded for small x using this expansion here. This expansion will play an essential role in the supercooled expansion, in the improved supercooled expansion, as we will see. So the production of true vacuum bubble is described by the time-independent bones. So we can describe the vacuum decay rate with this expression, where S3 is the bounce action that for time-independent bounds takes this form, and the time-independent bounds is simply the solution of this differential problem. Now, let me tell you some properties, interesting properties of phase transition in RSB models. So in RSB models, phase transition are always first-order phase transition. And first-order phase transition in RSB feature always a supercooling phase. So the temperature drops much below the critical value before the bubble nucleation became effective. And this ensures that at relevant temperature, the thermal collection are small, and the zero temperature mass is much larger than the thermal mass. So the thermal mass, so we avoid the infrared in the problem. So we can safely use perturbation theory. First order phase transition RSB models are always strong, so the PT release a large amount of energy. Okay, so now we're ready to introduce the supercooled expansion that have been developed in this paper here. And the idea is simple. If the supercooling is strong enough in a generic theory of the form we saw before, to a good accuracy, the full effective action for relevant value of key can be described by 3 and only 3 parameters, key 0, beta bar, and G, where G is defined as follows and can be thought as a generalized coupling of the field of the theory to the flat direction key. The condition for supercooled expansion is that this parameter epsilon, that is defined as follows, is smaller than 1. So the leading order of the supercooled expansion corresponds to approximate the effective potential truncating the thermal function at linear order. So if we plug this expression into the effective potential expression, we get this simple expression here and this very simple expression for the bounce action, where we have introduced 2 parameters that depend on the temperature. And as you can see, everything depends on the 3 parameters of the supercooled expansion. It is possible to calculate several first-order phase transition parameters. In particular, the 2 relevant for our discussion is the nucleation temperature that is defined as the solution of this equation, while the inverse duration is defined with this expression here. So the nucleation temperature Tn is obtained by solving this equation, where we use several approximations. For example, we use that the nucleation typically occur in this case during the inflation due to vacuum domination. So we can approximate it in this way. Moreover, we are assuming a large supercooling, so this parameter x is large, and this equation here for large x became something like this, where C and A are parameters that are defined only through the 3 parameters of the supercooled expansion, and this can be easily solved, and we get this is simply analytical expression for the nucleation temperature. So the inverse duration for the inverse duration is the same. We can plug the expression of the vacuum decay rate inside the definition of the inverse duration, and what we get is the simple expression here. And well, the leading order approximation means neglect the terms of relative order square root of epsilon. So we can go to the next to the leading order expansion by including this term in the expansion of the thermal function, in the expansion of the thermal function. So putting this together, we get next to the leading order effective potential that includes a cubic term that is perturbative. So this is the effect of this cubic term is smaller than the effect of these other 2 terms that we obtain at the leading order. And notice also that at the next to the leading order, we have to include another parameter. So in the next to the leading order, the parameter that we need to describe the first order phase transition in the supercooled expansion are four: K0, beta bar, G, and G tilde. That is defined as follows. Notice that this also is a generalized coupling of the fields to the flat direction, but this time it's only related to the bosonic degrees of freedom. The supercooled expansion generically breaks for epsilon of order 1 because it's valid for epsilon of less than 1. But there is an exception. In fact, it is valid for epsilon of order 1 only if the number of degrees of freedom with dominant coupling to the field key is large, since the two generalized coupling scale with the number of degrees of freedom in this way. So we have that despite the epsilon parameter is of order 1, the cubic term gets suppressed, in the effective potential gets suppressed by a factor that is at most of order 1 over square root of n. Moreover, 1 over x is still small for epsilon of order 1 since beta bar is loop suppressed, so this means that x is large. And it still makes sense truncating the small x expansion of the thermal function up to order 3/2, because the higher order terms involve smaller and smaller coefficients. So we expect that all the correction are still small. All the correction higher than the leading order are still small. So this is just an exception, because in general, when epsilon is of order 1, the supercooled expansion breaks. And this means that in the effective potential, the cubic term cannot be treated as a perturbation, and this equivalently we can say that the term x to 3/2 in the expansion of the thermal function is not perturbative anymore. So also if this perturbation theory looks that is going to break, we can treat the cubic term as a leading order effect. So we promote the cubic term as a leading order effect, and this means that we promote this term x to 3/2 as a leading order effect in the expansion of the thermal function, and higher order terms as a perturbation, as done in this paper here. And we can do that because in the expansion of the thermal function, the coefficient gets smaller when we go up in the order of perturbation theory. So we can promote the cubic term at a leading order when epsilon is of order 1. And this is what we call improved supercooled expansion. So the effective potential takes this form here at a leading order. So here we also have a cubic term. The action is this one here. And as you can see, since we are including the cubic term here, we have also to include the G tilde parameter. So we also need the G tilde parameter to describe the supercooled expansion. So in the improved supercooled expansion, we need 4 parameters. And well, we did a bit of rescaling here, and this parameter here is defined as follows. And for epsilon of order 1 is typically of order 1. So for the relevant values of epsilon, that is, there are those of order 1, we can express the three-dimensional Euclidean action in this way, where we use the result of this paper here. And this expression reproduces the numerical calculation at 1% level for the values of lambda lambda tilde we are interested in. Notice that by doing this, we are establishing the validity of this expression in a model-independent way within the improved supercooled expansion, since the model we are studying is a general RSB model. So we can solve this equation here, the nucleation, the equation for the nucleation temperature, that now takes this form here that has to be solved numerically. And we are interested in a small and real positive solution, lambda tilde n, for which this straight line reaches this function here from below in increasing lambda tilde. This equation does not always have a solution. So following the same step, we can also calculate the inverse duration that has this expression here. Okay. Now let me very briefly resume, tell you something about the late blooming mechanism. I won't go too much into the details. I just want to give you a very qualitative picture and then show you some results that are available in literature that we use it to make our calculations. So the vacuum decay is a probabilistic process. So there can be some region that persist in the false vacuum for a longer time than the background. So the idea is that since all the density energy that is related to the relativistic bubble wall behave like radiation, when the bubble starts to nucleate also in the late patch, so there is a delay between the nucleation outside the late patch and inside the late patch, and when the bubble nucleates in the late patch, density contrast between the radiation energy between background and the late patch can eventually reach a critical value delta C that makes this perturbation collapse. This is the idea. Now,
sorry, I have one question. Are you sure that delta C is a good criteria for this case?
Oh yes.
Delta C is a simple criteria in the context of inflation and other context. Maybe, right? And in this Supercooled case, are you sure that delta C is also a good criteria?
Well, there have been some discussion around this point. What I can, as far as I know, this perturbation, density perturbation, can create the curvature perturbation that are needed to collapse. But the point is that, well, we will adopt a value for this delta C that is 0.45. But in literature, I think that there is no agreement in this case of what value of delta C we can use. I think that we need numerical simulation about this point. But yes, there are some discussion around the use of the density contrast criterion in this case. Yes, we can study the late blooming mechanism by expanding this expression of the vacuum decay rate in this way. This is a very common. Expansion when one studies first order phase transition, and we will follow the results of this paper here by Guttenwar and Folansky. In particular, they found this result, this probability of collapse for alpha large for a very strong phase transition, and they found that this depends only on the inverse duration of the phase transition. As I said, we adopt delta C equal to 0.45. They also found this expression for the fraction of primordial black hole produced and the mass of these primordial black holes. This TEQ is the temperature at equivalence, so the temperature of the universe when the vacuum energy density is equal to the radiation energy density. So we can do more. It is also possible to calculate the spin of the initial spin of this primordial black hole. We will follow this result by Indra, Kumar Banerjee, and Arada, and we will use this nice expression for the initial spin that, as you can see, depends only on the fraction of primordial black hole and the mass. So it's completely calculable within the results of Guttenwar and Folansky. Now we are ready to express all the physical parameters of the late blooming mechanism in terms of the parameters of the supercooled expansion. So as you can see, we can find an expression for the equivalence temperature, for the mass of primordial black hole, Abel rate. We have two expressions for the inverse duration, depending on if we're using the supercooled expansion at the leading order or the improved supercooled expansion at the leading order. And then we are ready to calculate the fraction of primordial black hole and the spin of this primordial black hole. Now, before I show you the results, I'm going fast. Let me tell you something about this expression here. So this expression can be justified on the ground of the supercooled expansion. In fact, by using this expression for the temperature in terms of the time, and using the result we found for the bounce action at the leading order of the supercooled expansion, we find this expression here, and where x is, well, we already defined x as log of k0 over Tn. Now we can just plug everything into the vacuum decay rate and expand this fraction for T around Tn, obtaining this expansion here. Now this term, I mean this constant term, this leading this linear order term in T minus Tn, and this other one too, reproduce this expression here, while the other terms, so the higher order terms, are small. And this can be shown by, well, it can be shown that this expression here can be written in this form here, where gamma is this number and tau is an adimensionalized time respect to the time of the equivalence. And what we found is that this is typically small. This is small for the values, for the typical values of T minus Tn. In fact, if tau minus tau n is small respect to this quantity, this is a good approximation since, as I said, these terms are perturbative. This is also for the improved supercooled expansion, since beta bar is loop suppressed, and this means for epsilon of order 1, x is still large enough to make this suppression, so this term small to suppress the higher order terms in the expansion you saw before. So now let me show you the results we obtained. As you can see here, I got in this plot on the x-axis, we put K0, so the scale of the RSB scale, and this parameter here that is typically of order 1. And these results are obtained by using the improved supercooled expansion. We fix the two generical coupling to be equal to 0.8. In this specific plot, of course, one can make other choices. Then you see the constant FPBH line, so FPBH equal to 1 is this line here. So below this line, we are overproducing primordial black holes. Then there is the line for 10 to the minus 10 FPBH, and above this line, we produce less than 10 to the minus 10 fraction of primordial black hole. You see also the constant line for the mass and the constant line for the spin. And you see also this gray region here, where this gray region here is the region where the equation for the nucleation temperature has no solution, so it's not described by your approximation. And this is the region, this red region here is the region where epsilon is larger than 3. Now, for epsilon larger than 3, the improved supercooled expansion still works. This is just a benchmark to see what is the value of epsilon. Typically, the improved supercooled expansion starts to break when epsilon is around 10. Then you see the usual constraints on primordial black holes, so also the microlensing constraints, accretion constraint, mergers, and all the evaporation constraints. There is also a constraint on the reheating temperature. Now, what you can see here is a complete generic plot, because the parameters that we are plotting are generical and describe a generic RSB model. So, for example, if one wants to produce primordial, all the fraction of dark matter in terms of primordial black holes, one in every possible RSB model one can build, one should choose a value for the RSB scale that is between 10 to the 5, 6, 10 to the 8, 9 GeV, so in this range here. And this is a complete general statement. And also, if one wants to produce at least a fraction of the cold dark matter fraction of, in terms of primordial black holes, one should choose a scale for an RSB scale that is less than 10 to the 9 GeV, since otherwise the primordial black hole are all evaporated, because in this region of the plot the masses are all below 10 to the 15 grams. Here it is the same results, but using the supercooled expansion at the leading order. And as you can see here, in this red region instead is the red region where epsilon is larger than 1. And as you can see here, in this case, well, in this red region, the supercooled expansion is unreliable, unless there is a large number of degrees of freedom then coupled to the flat direction. In that case, the cubic term can be treated as a perturbation, despite epsilon is of order 1. And in that specific case, this region is still viable with the supercooled expansion. Well, this is another result using the improved supercooled expansion, but with a smaller value for the generical parameters, the generical coupling. And as you can see here, all the plot is within epsilon of less than 3. And well, this result actually is more evident in this plot here, where we use the supercooled expansion. So you see, in the case of the supercooled expansion, lowering G means also to open up the parameter space considerably. So the epsilon greater than 1 region is significantly smaller and less, well, and the supercooled expansion is more predictive in this case.
Can I ask a question?
Yes?
So in the region larger than 10 to 12, I expect some unexcluded region, because PPH is evaporate.
All PPH on the right of this line here should be evaporated. On the right. So this is what I was telling you. So if you want, in a generic RSB model, if you want to produce at least a certain amount of primordial black hole that can take to account a fraction of the dark matter present in the universe, then you have to take K0 that is below 10 to the 9 GeV. Otherwise, you are in this region, and in this region, black holes are all evaporated.
Yeah, but black holes evaporate. That model is much before BBN.
What do you mean?
Black holes evaporate much before BBN.
Yes.
That model should be okay. Is it clear?
If evaporated before, yes, you mean there is no constraint, physical constraint beyond this region? Yes, there is no physical constraint.
Yeah, I was asking why you cut that.
Oh, why I cut this? Well, because we typically take beta this parameter to be of order less than order 10, and we don't want to go too much to height to the energy scale here. So since the effect of the parameter, when you get lower values of this parameter, what you plot goes up in some sense. So if you look to this, the plots, this typically goes up. Then we just stop to plotting at K0 equal to 10 to 12 because, well, all the known constraints, at least the one, as far as I know, all the known constraints are this one here for the primordial black hole. So you can see everything at least. So here it looks a little bit cutted because the parameter G is small and the plot goes up. Okay, let me show you a zoom on this interesting interval for the value of K0. This is an interval that goes from the Lectrowe scale to 100 TeV. And as you can see here, the reported anomalies in the microlensing data of HSC fall inside this region, and this is general. This is general for every RSB model. Here we use the improved supercooled expansion with two different values of G. We can also make a plot for K-fixed. It was a bit dramatic because I chose a very small value of K0 and a very large value for K0. So you see that also varying G, what you face when you choose a very small scale for K0 is the constraint on reheating temperature, while here you face a constraint when K0 is large, you face a constraint for evaporating black holes. And this, is typically independent from the value of G when one chooses a realistic values of G. Well, this is the same plot, but using the supercooled expansion. As you can see from, well, this was clear also from the other plots. Typically, the improved supercooled expansion is more predictive because the class that the class of models that falls into the range, let's say, of the improved supercooled expansion is much larger. Okay, now let me do some a small example of a model. So we will extend the standard model with a U1 B minus L gauge group. This model was first described using the improved supercooled expansion in this paper here. Of course, it's a well-known model, but with the supercooled expansion for the first time, it has been analyzed here. And you can see the no-scale part of the standard model. We put a complex scalar in the theory that is charged under this group here and has charge B minus L equal to 2. We have we put 3 right-handed fermions, and as you can see, we have this Yukawa term of the right-handed fermions with this field A that after relative symmetric breaking will generate Majorana mass for these fermions, and this quartic coupling here that will generate the tachyonic term for the Higgs and for the standard model. So the complete gauge group of this theory is this one here. Now we choose as a flat direction the radial component of A, and we're ready to calculate the beta function of the quartic coupling lambda A that will look as follows. But well, then we put mu equal to mu tilde, so at the scale where we develop the flat direction, so all the terms proportional to lambda A go to 0. Then this term here is negligible respect this one, since we are choosing taking the right-handed neutrino Majorana masses below the electroweak scale, and also to match the measured mass of the Higgs, this parameter has to be small, so we can neglect it when calculating beta bar, and beta bar has this very simple form. The background mass of the new gauge boson is the following one. So now we are ready to calculate the collective couplings. So G and G tilde, there are the parameters of the improved supercooled expansion. And as you can see, these parameters take this very simple form, and in particular, they have this very simple relation. So G tilde and G are related, and this relation is specific for, I mean, it depends on the specific model, it's not general. In general, these two are, well, the relation between these two depends on the model, this is what I want to say. Then beta bar takes this simple form, and we then can calculate the mass of the scalar field key, and of course the mass of the Higgs boson here that takes this form here. Now we can plot the B minus L model. So since this parameter here, as you can see here, is constant, is 2/3. The model is is represented by this straight line, this black straight line, and for a value of key that is 2 times the 10 to 4 GeV, we can match the anomalies in the IISER data for this value of the coupling. And well, this is an example of how one can use the supercooled expansion to describe the first order phase transition. And this is interesting because all the results I showed are completely general within RSB models and are described by just few parameters. There are these 4 here for the improved supercooled expansion, or for the next to the leading order supercooled expansion, or just these three for the supercooled expansion, but in any case, there are just few. So the description is very simple. And we were also able to provide a model that can take into account the production of a large amount of primordial black hole. As you can see here, I mean, also if you don't look to this region, one can choose several values of G, and the B-L model still produce a considerable amount of primordial black hole. But this is just an example. One can try to do it with other RSB, specific RSB model. So I finished.
Thanks, Francesco, for this nice talk. So we have some time for questions.
I have a question about your question, beta 2 or something in the exponent of the nucleation rate.
This expression here.
Yeah, but before. Yeah. So is beta 2 positive or negative in your model? Maybe positive.
What? Sorry, is this positive or negative? This coefficient here.
Beta 2.
Beta 2. We didn't consider this. We just considered the fact that this is small. We wanted to understand if this is smaller than this one in the supercooled. I mean, if we can justify the fact that one can truncate this in the ground of the supercooled expansion, then we didn't I didn't do any assumption of the sign of this coefficient here.
Okay. Yeah, I was just wondering if beta 2 is negative, then it's easier to realize this data bloomer mechanism. But okay, we can discuss later. I will ask a question later.
Yeah, and sorry, I missed your talk for five minutes to go out. So can you show me the spectrum for the gravitational waves? The spectrum for the gravitational waves?
Spectrum of gravitational waves? There are no gravitational waves in the...
So you're only considering the curvature
the generation of primordial black holes.
So they will not have any associated gravitational waves?
I'm not presenting the results on gravitational waves today, but of course one can use the improved supercooled expansion to describe the spectrum of gravitational wave produced. For example, it has been done in the case for the gravitational waves emitted by the bubbles, by bubble collision. And as you can see, as long as you have an expression for the inverse duration, I think this is possible, but I cannot show you these results because I don't have it here, but I didn't, I mean, I wanted to present only the results on primordial black holes production.
Okay, so the reason I'm asking you this because it is not the same as the usual story of gravitational wave from bubbles, because gravitational wave from bubbles will of course be there, but because you have a source of curvature perturbation, that should induce a second order gravitational wave, just like there is a scalar induced gravitational wave in case of inflation. Here also, the UV of the tail, I mean the UV free frequency, so you should see the peak of the gravitational wave from the bubbles, but then you should not see the standard bubble falling down, because that should have some modification, because you're creating some amount of inhomogeneities that should at the second order level should modify the standard gravitational wave that you're saying. So your gravitational wave spectrum will be non-standard because of the presence of, because you have created large amount of inhomogeneities.
Oh, I see. Okay.
So that's the reason we're asking. And the second question I have.
Interesting. We can discuss. So
sorry?
What? I mean, it's interesting. We can discuss.
Yeah, sure. And the second thing I wanted to ask you is that can you go back to slide 24 or 27 where you had this expansion of beta 2? Yeah. So I think no, it's 27. Yeah, so here you're saying that the second order term, like the quadratic expansion beta 2, so for the supercooled case, you can neglect it to be small, right?
Yes,
that is
what I'm saying that this expansion is justified on the ground of the supercooled expansion.
Okay, so my question is that let us imagine we are studying, I mean, in the case of not supercooled or not ultra supercooled as you are showing, but still, I mean, at that, all the rest of the calculations for primordial black holes and everything more or less will go the same way, right? So you could still do the calculation and create primordial black holes, considering the fact that, let's say you have a scenario where beta 2 is significantly contributing to your nucleation rate, right?
Well, these results here are obtained using this expression here. So I think it's crucial when you try to cast this result.
Yeah, I understand that. So, so in this paper, they had neglected the effect of the
Yes, they neglect the effect of the
But I'm saying
quadratic.
that this is not true. This is wrong. So there will be scenarios where you will have significant deviation where the quadratic term will have.
But not in the supercool.
No, that is what I'm asking. It may or may not be in the
in this case, these terms here are produced by higher order terms in this expansion, and these are small for the interesting values that we used. Typically, we don't get too much far from tau n, and typically this factor here is way bigger than this. So this is small. So at least in the regime of supercool expansion, it looks like that this is negligible.
But can you tell me the physical reason? Like I can understand the algebra maybe. Like what is the physics of supercool that allows you to neglect that quadratic?
Okay, this is because we are expanding t around tn, so this is the expansion around tn. Well, no, let me do this by scratch. So we use this expression of the temperature in function of the time, and we plug it inside this expression here for S3. This expression here is obtained by the supercool expansion at the leading order. So here is where the supercool expansion came. So we get this expression here, and then we simply expand for t around tn. And expanding for t around tn, all these higher order terms are small because one can show that we can discuss about that. I don't have the sheet with the calculation, but it's a very easy calculation. You can show that this can be rewrite in this way, and this is this is typically smaller than this factor here. Because, well, this is the small number here, and x in the supercool expansion is always of this order here. So this is way larger than this for the interesting values of tau. And this means that this constant term, this term that goes like t minus tn, this other term that goes like t minus tn, reproduce this one. The other terms reproduce this term here, but these terms are all small because this is small. I'm showing you that this is small, so this is a small contribution. So it makes sense to truncating this, neglecting this contribution here. So if this contribution modifies our discussion, it modifies the discussion perturbatively in the regime of supercool expansion.
Had it not been supercool, those terms will not be small.
What?
Had it not been a supercool phase transition, those terms will not have been small.
If it's not supercool, probably. What I can tell you is that in the regime of supercool expansion, this is small.
Okay, thank you.
Any more questions, comments?
So in calculating the beta function means the particle physics beta function.
The beta function?
Yeah, the beta function. You took only coupling G into account. Is there any parameter region where lambda square matters?
Sorry, can you repeat?
So in beta function, you should have contribution from the Higgs, the scalar field itself.
This one?
So is there any parameter region where these lambdas become important in this beta function? So for example, when coupling G is small.
I think it could, it starts to be important when K0 starts to be small.
Yeah, so in the parameter region, you showed 1 over G squared, something like 1 over G fourth in the vertical axis. And in the upper region, I expect, in the upper region, coupling G gets smaller. So I expected that in some parameter region, coupling lambda is important instead of beta, no, instead of G.
I see, but I see your point. So you're saying that in some region here, up here, the lambda, that this coupling here becomes important.
Yeah, I was just wondering, yeah.
Well, the point is that this is typically fixed by the fact that we typically choose, in this model, in this case, we are choosing key to be large. So we have to meet the mass of the Higgs parameter, the actual mass of the Higgs. So if this is of order 10 TeV, 100 TeV, this has to be very small. Now, so you're saying that when this parameter starts being small, this is comparable to this? You're saying this?
Yeah.
Oh, but this is fixed. G is fixed. So in this region,
okay.
in this plot here, this does not. This is small. These are always small. But yes, of course, if one wants to analyze the model properly, one should take into, properly. It depends on the setup. If the setup is a setup where this becomes important, the analysis should be done in a more detailed way. But in this particular case, this is always small. It doesn't play any role in any case because G is fixed.
Thank you.
Okay, so if there is no more questions, let's thank Francesco once again.